Welcome to homework.
So for this question, we're trying to show that a simple graph with n vertices must be connected if it has greater than greater than n minus 1 times n minus 2 over 2 edges. So one way to do this is to show that if this simple graph, so our logic is if the graph is not connected, then the max number of edges is n minus 1 times n minus 2 over 2. That's one way to solve this problem, right? Because if the max number of edges in a non-connected graph is this number, then that means that if you have more than this number of edges, then you must be connected. So that's essentially the overview of how we're going to solve this problem. So without loss of generality, suppose that the graph is not connected. Then let's say one component has k vertices, where k is just a number from like 1 to n minus 1. So k vertices in one component. That means that there are n minus k vertices split among at least one other component, right? We don't know if they're all in a separate component or if they're like all separate. At least one other component, right? So if we show that this graph can't have more than this number of edges, we're good. So we want to maximize the number of edges in this graph, in the graph above, right? And the way to do that is by assuming, right, as we said before, the maximal number of edges in a simple graph occurs when the graph is complete. And so let's assume that this is a complete component. So if we maximize that, we get that we have k choose 2 vertices in this complete component. And then to maximize the number of edges in this, we assume that they're all in one component and that it's a complete component as well. So we've maximized the number of edges in this graph by assuming that both of these components are complete. And then that gives us k squared minus nk plus n squared minus n over 2. This is the maximum number of edges in this graph. And so we want to maximize this expression, right? So we realize if we look at this is a parabola shaping upward, right? If we find its vertex occurs by calculus at n over 2. We just take the derivative. So we would get 2k minus n is equal to 0. So n is equal to k over 2. No, k is equal to n over 2, sorry. And so our vertex is here. That means that its maxima will be at the bounds, right? It'll be greatest farthest away from n over 2. So we know that the domain, right, for k is 1 to n minus 1. Luckily, that's symmetric about n over 2. So basically, this expression, right? So in other words, this expression in quotation marks is maximized at k equals 1 and k equals n minus 1. They will both give us the same answer. So let's see what this evaluates to at k equals 1. So k equals 1, this expression becomes 1 minus n plus n squared minus n over 2 is equal to n squared minus 3n plus 2 over 2 is equal to n minus 1 times n minus 2 over 2. Voila. So in other words, the maximal number of edges in a graph that has k vertices in one component and n minus k vertices split among at least one other component is this number. So we found that the max number of edges in a disconnected graph on n vertices is n minus 1 times n minus 2 over 2. And we're done, right? So in other words, if you have more than that, if you have more than n minus 1 times n minus 2 over 2 edges, you must be a connected graph. And that's what we're looking for. So to review, a simple graph is connected if it has more than this number of edges. So we flipped the problem on its side and we were like, okay, how can we look at this from another lens? The other perspective is that if the graph is not connected, then it can't have more than this number of edges, right? And so that's what we were seeking to show. So essentially, we assumed that the graph was not connected. In other words, it had k vertices in one component where k is between 1 and n minus 1. And the other n minus k vertices are split among at least one other component. So if we show that the maximum number of edges in this graph is this number, then we're done. All we have to do is maximize the number of edges in this graph, which we have done by assuming. So the way to do that would be to assume that this is one component, it is complete. That will give you this many edges. That's the maximum number of edges in this component. And then to maximize this part, we assume that these n minus k vertices are all in one component and they're all complete. They're all connected with each other. So the maximum number of edges, we get this expression. And then we need to maximize this expression for k, for the domain in which for k is between 1 and n minus 1. And so we realized that the domain, that the parabola is maximized at k equals 1 and k equals n minus 1. And so the maximum number of edges is once we work it out, n minus 1 times n minus 2 over 2, and we're done.